Hi, welcome to Truecaller. I hope you're enjoying your time and meeting people outside your normal circle. So I will start by presenting live caller ID lookup and how we made Truecaller work finally on iPhone. I'm Ahmed Elnaqah. This is my LinkedIn, and I am the iOS tech lead here in Truecaller. I have been working in Truecaller for 7 years now, and I work on many projects within the iOS domain here in Truecaller, and this is by far the most exciting project I participated in. So, I will start by Truecaller purpose and then go through the different approaches that we followed for caller ID. And then I will explain what is the live caller ID lookup. And finally, I will take your questions in the end. So let's start with what's Truecaller purpose. So Truecaller main purpose is to protect you from scam calls, and of course not to get scams. Identify businesses, legitimate businesses like Uber driver, Amazon, whatever, who someone is calling you from your bank. And then to enable different users to identify each other. So if you create a profile, you provide a name, and whatever name you provide there, it will show to the other users when you call them. So how did we approach the caller ID? Since the beginning, it was a bit disappointing because Truecaller was very limited on the iPhone, on the iOS, because of the operating system limitation. So you had to open the app, search for a phone number whenever you receive a call. And this was a bit disappointing. And then in 2016, Apple finally introduced something that we can hop on, like call directory extension. And this is the first time that we had caller ID for Truecaller. And how this works is actually it's run a different process, an app extension, and this process feeds a list of contacts inside the iOS directory. And this directory is shared between us and many apps. Whenever the phone receives a call, it consults the directory for these numbers, and then if it finds it, it shows a name. If it doesn't show anything. So this is how it works, but it has some challenges and limitation. So let's talk about that. So first thing, it has a limited number of contacts that you can feed to this app extension, the call directory extension. So we had to provide multiple call directory extension. And also because we had different sources for those data and we wanted to segregate the logic, this was a reason for that as well. And this introduced a challenge on how we onboard our user. The user needs to go open the settings and enable each extension by itself. So it's not as easy as it should be. When you enable the extension on the client, we download a full list from our servers, and then this list may fail, and we need to handle failure, and this happens in another process in the background. Also, when we download this list, we feed it to the call directory, and this may fail for many reasons. Apple has a lot of restriction due to how they load the list in the directory, and this also may fail, and then we have to handle this failure in the background whenever the extension is triggered. To keep your list updated, we introduced the background task scheduler, which run in the interval, and this is of course based on the user behavior, on how the user is using our Truecaller app. And if they are opening the app enough, our app gets scheduled and get time in the background. Otherwise, it doesn't. User may disable background refresh to keep battery usage to minimum, and then we don't update the list. And then when you receive a call, you get like outdated information or something that you didn't expect. Another approach is we introduced in 2023 is running a shortcut, Siri shortcut. You can trigger it from different setup, like either from the side button or with double tap or whatever, or Siri call Siri to search Truecaller. And then it takes a screenshot, use OCR to try to extract the number, search Truecaller app, and then show an app intent in front of the calling screen. And this was working very cool, but it required a lot of steps to set up, and yeah, it required a user action to identify the phone number. which of course, it takes some time to run the shortcut as well. So let's go to the live caller ID lookup and how it's working. To explain that, I will go through first introducing what's live caller ID lookup, then talk about how this new system preserves the receiver information, and how we preserve the query itself, which is the phone numbers that you're searching for. And then I will discuss some performance criteria. So let's start with live caller ID lookup introduction. Live caller ID was introduced in iOS 18 last year in WWDC 2024, and it's only supported from iOS 18. It shows as an extension, another extension like call directory extension in your settings, which means that you need to open the settings and enable this extension as well. When Apple introduced it in their feature document, they actually mentioned that they built it for apps like Truecaller. So it was actually built for us to be able to provide our experience on iPhone. Yeah. So how it works? Once you enable the extension, we provide our service URLs and tokens to the operating system so it can communicate with our service. And this is basically what the clients do from this side. Like it provides, from our extension, we provide this URLs and OS token, and then the iOS handle all the coming steps. So basically, when you receive a call, the iOS should make a query to our service and just receive the identity for the phone number. As simple as that. What's the problem then? So the problem is we need to keep the user privacy preserved. So when a caller make a call to this receiver, the number show, and then it takes the number, makes a query. So here, in the query, we expose the caller number. And this is something that we need to hide. And second, the user identity, which user received calls when. This is something that our services doesn't need to know. Like if you receive a call from someone, we don't need to know when you received the call and for what and from who. And this is the information that we need to hide. Yeah. So let's first talk about how to preserve the receiver information. So the one who's receiving the call. Basically, Apple will put app relay between us and the clients. So the device will communicate with an app relay, and then the relay will communicate with our service. They are using a protocol called oblivious HTTP relay. What it do, it masks all the information from the request, like IP address, where it's coming from, any information that can refer the user, even the authentication headers. So it doesn't show us anything in our service. All we know is we communicate with app relay, and app relay communicate with the device, do even device attestation, make sure that it's an iPhone. And for app relay not to be invasive in our privacy and see our request, this protocol uses encryption. So the user encrypts the packet, the request itself, send it through the relay, we decrypt it with our keys, and then serve it to our service, and same, vice versa. We do the same to send the request to the user. And this is how the app relay is stay oblivious. This is the oblivious part from HTTP relay. So there is a problem here. Is it really a Truecaller user? How would we know? So all we know is it an app relay communicating with us. Anyone who's using the app relay can reach to our service, use our service without us knowing if it's a Truecaller user, and it's allowed to use our service actually. How to solve that? So we used another protocol called privacy pass issuance protocol. And this protocol, by the way, I forgot to mention that there is the QR code for the RFC, request for comment document from IEEE for those protocols, if you want to scan. So privacy pass issuance protocol allow Truecaller to build an issuer. This issuer issue tokens, and those tokens you can think about it as Truecaller currency. So whenever a device requests tokens from our issuers, we give a bunch of tokens, and each token can be used for one request. Once we get this token, we validate it with the issuer to make sure that it's token generated by Truecaller issuer. But all the tokens are anonymized on the device. So we can't differentiate between tokens. We can't know which user got which token. We can't associate the token with the user. So basically, those tokens are all the same for us. we can only verify that this token was generated by our issuer. So our issuer is basically a currency issuer, and then we give this currency to the device. The device should use it one by one with each request, and then we get it, validate it, keep it to make sure that the user doesn't, or the device doesn't use it again. So token can be used only once. And this is how, combining those two systems, we can hide the user identity, but make sure that it's a Truecaller user, not anyone using our service. So we already can, like this, we already preserve the receiver information. Let's talk about how we preserve the query itself. To explain that, I need to explain something called homomorphic encryption. Who here knows what's a homomorphic encryption? Okay, then let's start to explain it. So for explaining that, I will go through an simple accounting example. So let's imagine that you have an app that that calculate your net salary from your gross salary, but you don't want to share your salary with our services. So this is the app. You will put your gross salary, very big salary, encrypt it. The client will encrypt it, send this encrypted gross salary to our service. The service will apply mathematical operation on the gross salary, get the net salary as an encrypted result, and then send it back. And then the client can decrypt this result and get actually the value. So basically, homomorphic encryption is a characteristic of encryption algorithm that allow you to apply mathematical operation on the ciphertext the same way that you apply it on the value itself, and get the same result while it's encrypted. And by doing that, we can apply complex operation in our service without the user exposing any information about the data that he gives us. So how do we use that with our problem? We have phone numbers in our database, and we want the client to query a specific query without us knowing. So there is two parts here. The first part is we need to convert our data or encode it in a way that we can do mathematical operation on this data. The second part is we can't know about the query. So the user need to understand how our data is formatted, so it knows exactly which part of the data that it need to pick. We can't be the one doing query on our database. The client need to be doing query on the database. So how do we do that? We share the data information. So let's say that we have our data and we split it to shards. Shards means like chunks of the data. Let's say that we split it to 8 shards. And then every shard has inside it 24 buckets. And then we bring our data, which is phone numbers, contacts, and based on the phone number, we will consider the phone number as the key. We will fill all those shards with the phone number based on a sharding algorithm, like a sharding function. So we know exactly, based on the phone number, which shard it will go to and which bucket inside the shard it will go to. So we have this division. We share this information with the client. So now the client know exactly how we placed the phone number inside our data, inside our database, in the shard, inside a bucket. So let's say the client have a phone number and it knows that it should be in shard number 3, bucket number 11. And basically this will be the query. So this is the query from the client. Let's talk about how can we apply a mathematical operation with this query. So if we get our shard, which has 24 buckets, and for simplicity, let's say that we will serialize it to an array, where each element in the array is 1 bucket. How would you, if you want to get bucket number 11 from this shard, how would you do it? How will your query look like? It probably will look like something like that, where you mask everything else and just get bucket number 11. So we will have an array of binary, and then we will dot product it or multiply it with the shards that we have. And this should get us the result, which is 1 bucket, the exact bucket that we need. So in this way, we formatted our data in a way that we can apply mathematical operation on it. And we know how the query should look like, or the client know how the query should look like. So if the client knows that needs shard number 3, bucket number 11, it will form the query to fetch bucket number 11, and then encrypt it, add the information that it needs shard number 3, and send this request to our service. Our service will fetch shard number 3, apply a mathematical operation on that, which is encrypted, get an encrypted bucket, send it back to the client. The client will check for the phone number inside. It can be a hit or miss. So it will get the bucket anyway. And by doing that, actually, we achieved an encrypted or a private information retrieval of the phone number. So let's talk about the performance criteria. So as we know, which shard exactly the user asked us to apply the mathematical or the query on, the size of the number of phone number or the number of contacts inside this shard matters actually, because the lower the number of contacts that you have inside a shard, the more information you can expose about the query. So if you have 10 numbers, for example, inside one shard, this means that you can predict the phone number is within this range. If you have 1,000 number, it will be harder to predict because this is the shard. So the more numbers that you have inside the shard will affect your mathematical operation performance, because it will take more CPU resources. It will be harder to calculate, but at the same time, it will make the query more private. Second thing is the phone do 2 requests every time, one for identity, one for block. The block request need to be within milliseconds because it need to like do the round trip, like it need to be received before even the iOS show the calling screen on the screen. So decide if it block it or not. The identity request need to be within the ringing time. So whenever the phone is ringing, we need to receive the identity request to be able to show an identity. And of course, if the response time is slow, this means like like bad user experience. If it's faster, it's better user experience. So this is how we manage it. The iOS will always do 2 requests, identity and block, to avoid the service from knowing exactly if the user received a call from this number before. So let's say the user received a call from the same number twice. The first time it will catch the identity. Second time maybe it will ask for the block. But every time it will do 2 requests just to hide this fact. So it doesn't give any information about the client, which means, of course, your service will need to handle more requests, which means it will be more expensive. To have a very quick response, it's recommended that you keep the shard in memory. And this is to avoid like loading the shard from database or from file system and then serialize it, put it in another structure, apply the query on it, like do all this. So it's better to keep all the shards in memory and then apply the query once you get it. And this, of course, will limit the scalability of your server and which requests go to which node. Yeah, one thing I need to say here is this is the first time in this scale that private information retrieval is applied in any production app that we know of. Thank you. And this is how it looks on the iPhone. So a spam call or a business call. We provide the information that we provide is basically a name, a category, and an image. And of course, the caching time. So the TTL for how long the iOS should cache it. And this is a bonus promotional video that I want to show you from our marketing team. How to play it. Yeah, I lost my mouse. Huh? Sorry. Thank you. Those are links for the open source repos that Apple provides. This is an example for how to use the live caller ID. And this is a Swift homomorphic encryption. It's in Swift, which means that we actually currently running Swift code in production on our backend to support this feature. Yeah. Questions? Thank you. If you have any questions. Yes.
Thank you, Ahmed. Your work seems interesting. It's okay. It's okay. I think people can hear me. Are you recording? So I need to speak in this. Okay, I will speak in this. Maybe you kind of like answered my question with these URLs at the end. So, but is it like Apple just gave like an API to you and said like you can use this, but don't send anything identifiable to us? Or there's like examples and you were collaborating, and how did you test this that is working?
Yeah, I would say it was very challenging to test. Like they have those two repos. This is an example of how it works. You can run it locally on your machine and test it with the iPhone and build the extension and just test with it. We started with that, of course, and saw how it will go. And we started reporting a lot of issues on Feedback Assistant, and got resolved some of them, some not yet. But yeah, it was challenging to do this project because you need to design it yourself. You need to deploy it based on your data scales and how you're gonna provide this infrastructure, and how are you gonna serve it to this amount of users. So I would say that we started with this, but this is not the solution that we ended with. We ended with a totally different solution for our scale. And it was a lot of experiments and a lot of tests and a lot of problems that we try to solve. And we're still working on it. So it's not like done yet. So it's still improving by time. We're trying to do it. So Apple provided this Swift homomorphic encryption library, which provides the base code for the encryption of the query, and applying the query on your data itself and how to process your data. It allows you to process your data in a certain way that it can apply homomorphic encryption on. And then we use that in our backend based on our scale in the way that we see fit, not based on the example. And then we serve it like that. Thank you.
Yes, thank you for presentation. Just two quick questions, maybe. If you can, maybe, is it possible to change the slide to the one where you're sending the request, two requests simultaneously? Yeah, just next one, I think. This one, yeah. Oh. Yeah, so you said these two requests send at the same time, right?
Yes.
And identity and
Yeah,
blocking, right? So how you, so there is slightly possibility of race conditions for these requests. Is it still something for you, or you can manage both, separately without getting the other one response or something?
No, so I would say that it's not us that's sending those requests. Everything, when I talk about the client on all the other slides, it's always the operating system. And those are two different network requests. We handle them differently. So those are two different use cases. So whenever we receive a request, we respond to it. We don't treat it as the same. We don't link it in the backend together. So each request is served in its own data. So blocking data is different from the identity data. Identity data, we provide name, photo category. Block request is applied on a different kind of data, which is basically 1 bit, 1 or 0. Do you need to block or not?
Okay, so they are not really like connected. So it's
no.
just, you need both for final, showing the final UI and this.
Exactly. That's the operating system always do two requests whenever it receive a call. It never do one.
Okay, thank you. And the other one, just the charts that you showed, I think the previous slide. What was it? Yeah. Yeah, but yes, exactly. So we can use this one. That's
Yeah.
fine. So basically, shards you said for make it a bit faster, the algorithm to send it or identify. You have to store it in a memory, right?
Okay. Yeah. So you're talking about this one. Yes.
Yes, in memory storage.
To get a very fast response.
Yeah, and these shards, they represent, or each this shard contains some user information, if I understand correctly. Or,
Yes.
so some maybe sensitive user
Yes.
information.
Numbers and names.
Yeah, and so my question is that since they is stored in memory, if I understood correctly, they then encrypt it later, right? For the request. So in memory, they stored without encryption, if I understood correctly.
They stored encoded in a way that that we can apply mathematical operation directly on them. So they are not stored in plain text. They stored in an encoded way, which is if you go through the repo for the Swift homomorphic encryption, you will see that they are storing it in something called Cocoaheads table. And then they keep it in memory. And then when you apply the query, you can apply mathematical operation, which matrices operation basically on this data.
Okay, so yeah, they kind of encrypt when you're storing in memory, if we can, or
yeah, it's not encrypted; it's encoded, so it doesn't have a key.
Mhm.
So you can reverse it, but reversing it is not as easy as it shows.
Yeah, of course.
So basically, you don't have the phone numbers; you have the hashes of the phone numbers as the keys.
Yeah.
So it's stored in a way that's hard to reverse, but it can be reversed because there is no encryption key for that.
Yes, yeah. Asking just because in past there was some, malware attacks for them in memory specifically, when you can read what is stored in the memory, the entire chunk, and then get some information from that.
Yes, of course you can accept the delay, the latency, and fetch it from a database if you want. You can. There is different approach based on what do you expect, how your resources look like, and what's your infrastructure is based on.
Yes.
So of course you can. There is a lot of compromises that you can do here for security, for data protection, for your infrastructure, for cost, of course.
Yes. Yeah. Thank you for your answer.
Okay, I'm just wondering, how does this new solution compare to the old one in terms of like load on your backend system and stuff like that? Is there? I mean, now you get 2 calls, right, for each iPhone call.
Yes. So the first solution is the call directory extension. So the call directory extension actually wasn't. We weren't receiving requests when the iPhone receive a call. So it was like we load a local database on the device, and then whenever a call is received, the device check with this local database. So it was limited on number. We can't like add all our database on the device. We need to like select a certain amount of numbers and put it on this local database, and then the iOS will advise against this database and then show the name if it exists. It was just downloading this. Let's say that whenever there is update, it was downloading this list from our service, and that's it. We don't receive any request based on call. But in this service, we actually receive requests based on call. Whenever there is a call, we receive 2 requests, and it makes the data live. Like you can always update your data and keep it up to date. It doesn't depend on the local storage anymore. But the call directory extension, we still use it because this provide an offline experience where you don't have internet on your device, for example, or something like that. And it also offloads the load on our services, because if the number already exists in the call directory extension, it will not trigger the request to the backend.
Thank you.
Hi, thank you for the great talk. 2 questions for you. One regarding the tokens that you mentioned, right?
Yeah.
So you said there's a limited amount of tokens on device, and that once it's consumed, it can be revalidated and added, right? So my question is, when does that process happen on the device? Is it when the user reopens the app, or is it in the background? How does it?
No, it's actually the iOS daemon. So it's not our apps that do all this. It's iOS itself. So it
Mhm.
goes to our issuer, generate new tokens whenever the reserve is the cache is about to get empty. Let's say that they have a threshold. They have like 10 tokens, and if it's less than 5, they go fetch new tokens. And of course, we provide limitation for our issuer. Like for user, for example, we generate a certain amount of token based on rate limiting that we decide. We can do it differently for different type of user, like free, premium, whatever.
Yeah. And one more question. When you said that the client is the one that handles all of the querying on its site, and then you clarified that the client is always the operating system itself.
Yeah.
My question is, what do you exactly provide in your extension to the operating system itself? Because like, is it just the algorithm? What is it exactly that the OS requests from you?
No, it's only the extension only provides the URLs for the issuer and the service, and the tokens that it need to use, the device, the iOS need to use to issue tokens, to issue new tokens. And then the operating system communicate with the service and ask for this configuration, which is how the data is divided on our service, and then we provide it.
So it fetches all of those configurations from the service.
Yes, itself. Yeah.
Perfect. Thank you.
Thank you.
Thank you for a great talk.
Thank you.
I am curious regarding the extension that you have, the shard memory consumption, and if the call directory extension has the same severe memory limitations that other extensions have. Like if you have a keyboard extension, it's memory capped at 50, 60 megabytes.
Yeah, I think the limit was 12 megabyte for the call directory extension, if I'm not mistaken, or 14 megabyte, something like that. So yeah, it was challenging at the beginning to how to load all this data and without actually loading it in memory and releasing it immediately, and keep loading it in the call directory extension. Yeah, we faced a lot of challenges with memory limitation on this extension, and the problem is whenever you do some things, a bug is very localized on the device. That's very hard to track, and it's very hard to expect what happened while doing that. But
did you get any response? Like, have you reached out to Apple regarding the memory limitation and see if they can?
No, we
consider to
actually
increase it?
we actually implemented our own way of loading this list and handling it in a way that we don't pass the memory limitation. We never actually needed the extra memory. It was the easy way to ask for extra memory limitation, but to be honest, we managed without it. Like we were able to load a lot of numbers in this call directory extension without even passing this memory limitation.
Thank you.
Thank you. Any more questions?